Hello everyone, this is Achintya Medhi. So in this video, I'll discuss about electromagnetic radiation, region of spectrum, Doppler Protein, collision protein, and Heisenberg uncertainty principle. If you like this video, please subscribe my channel and share with your friends. So spectroscopy is basically all about interaction of electromagnetic radiation and matter like any substance in any phase, solid, liquid, gaseous phase, molecule, atoms. So electromagnetic radiation will interact with matter and show some emission spectra, absorption spectra like this. So first of all, we have to know what is electromagnetic radiation. In electromagnetic radiation, there are two elements there. One is electric field and one is magnetic field. So there will be two waves propagating in such a way that they are perpendicular to each other. That means this is EC plane. There is a EC plane which is indicating that electric field, and this is MC, which this plane indicating that magnetic field. Okay, in electric field there will be a wave in the plane of EC. There will be a wave propagating in this direction. Okay, and in magnetic plane also, magnetic field, there will be a wave propagating in. So these are produced by the oscillation of electric charge and magnetic field residing on the atom. And this type of radiation can travel through vacuum also. Okay, and this electromagnetic radiation are simple harmonic wave. It is trivial to show that any simple harmonic wave has properties of sine wave, which is defined by y is equal to a sine theta. To explain simple harmonic wave, let's consider one particle which is moving in a circular wave, circular motion. So a particle which starts from this point O, okay, and reach this point P. The particle when reach this point P, there will be a angle theta. Okay, and when the particle is in this point O, there will be no displacement. That means no angle theta will be 0. Okay, and there will be no displacement. So the wave will start from this point where displacement is 0. Okay, when the particle P reach this point P, then there will be a angle theta and displacement will be y. Okay, and here in this wave you can see that the displacement is y here. Okay, so when the particle reach this point where the angle will be theta is equal to 90, and as we know that sine theta, if you can put here y is equal to a sine 90. Sine 90 is equal to 1, so it will be a. So displacement will be a, y is equal to a, which is the maximum displacement for the particle in the wave. Okay, and this point indicates this point where the wave has the maximum displacement a. Okay, next, when the particle will move in this direction, so again gradually the displacement will be lower. Okay, when the point P reach this point, the particle reach this point, the angle will be 180, and 180 means 0. Sine 180 means 0. Sine 180 is equal to 0. So at this point y will be 0. Okay, and that point is this one. Okay, this is twice, this is pi, angle pi, and this is pi by 2. Okay, and this is the time graph I'll explain later. So this is pi, and when the angle is pi 180 degree, the displacement will be 0. Again, the particle will move in this direction, and when it will reach this point, that means this one, okay, at that point the theta will be 270, and sine 270 degree means minus 1. So y will be is equal to minus a. So displacement will be maximum, but the phase will be opposite. Okay, so I will write minus a here. Okay, next again point, when the particle moves in this direction and reach this point, at that point the angle will be 360, and sine 360 means again 0. So again y will be equal to 0. So at that point, which is twice pi, okay, that means we have got 3 points here, 0, pi and twice pi. At these 3 points the displacement will be 0, and I have obtained 1 point here and 2 point here, on which displacement will maximum. Okay, and which those are, this is pi by 2, and this is twice pi by 2, twice pi by 3, oh, sorry, 3 pi by 2. As the particle moving in a circular motion, so there will be a angular velocity, which is denoted by omega. So angular velocity omega is equal to theta by t, or we can write t will be equal to theta by omega. So here this is the time axis here, and this point indicating that this is pi by time as t here, and theta is pi, and omega will be angular velocity. So here it will be pi by omega, this point indicating pi by omega, and this point indicating pi by twice pi by omega. So it is concluded that at the point twice pi by omega, when the wave has completed, okay, this is a complete one wave. Okay, so in this wave the particle complete one circle. When the particle complete one circle, we will reach this 0 displacement, and which is at time twice pi by omega. Okay, so you can say that after twice pi by omega time, the particle will complete one circle. Okay, that means twice pi by omega second, in twice pi by omega second the particle will complete one circle. Okay, now in 1 second how many circle will be completed? It will be 1 by twice pi by omega, that means omega by twice pi circle. Okay, so in 1 second omega by twice pi circle is completed, and in 1 second means what? That means this is a rate. That means in 1 second this number of circle is completed, which is, we can say that, frequency. Okay, this is frequency, and what is the frequency? Omega by twice pi per second. Frequency is equal to omega by twice pi second inverse. Okay, so we can write omega by twice pi is it is frequency denoted by nu. So omega will be twice pi nu. Again I will write y is equal to a sine omega t, and we can write sine twice pi nu t. That means this nu omega is equal to twice pi nu. So I have put here instead of omega I put here twice pi nu. Okay, and so this is one of the important equation. Y is equal to a sine twice pi t. Okay, again this length from this point, from this 0 to this twice pi omega, this length is called lambda wavelength. This is one wavelength. From the adjacent crust to crust or trough to trough. Okay, this is tail, you can say tail here. It is one tail, this is one tail. These are two adjacent tails, and the distance between two adjacent tails, it is called wavelength lambda. Okay, and this lambda is obtained how? When the particle complete one circle, and when the particle complete one circle, we have obtained one wavelength. Okay, now if the velocity is c meter per second. Okay, c meter per second, that means in 1 second the particle travels c meter. 1 second particle moves c meter. Okay, now as I have seen here, in 1 second in 1 second omega by twice pi circle has been completed, which is denoted by nu. Okay, now that means in 1 second there will be nu times of lambda, or you can say that in 1 second, as omega by twice pi circles are completed, so you can say that in 1 second omega by twice pi lambda wave number of waves will be there. Okay, so you can say that here in 1 second there will be nu lambda, new number of lambda. Okay, so that means in 1 second c meter travels, and in 1 second there will be new lambda length. So this c and new lambda will be equal to each other. So we can write c is equal to new lambda. So nu will be equal to c by lambda. So in this equation I will put the value of nu. So y is equal to a sine twice pi ct by lambda. Okay, so this is one of the important equation through which with the help of this equation we can solve some problems. Again, there is one very important term, which is wave number, which is denoted by nu bar, and nu bar is equal to 1 by lambda. Reciprocal of wavelength is called wave number, and the unit is centimeter inverse. Okay, so after knowing what is electromagnetic radiation, now let's discuss about region of spectrum. So when electromagnetic radiation interact with matter, which are made up of molecule or atom, and those atoms or molecules have some energies like electrical energy, translation energy, vibration energy, rotation energy, like this. We can separate them, those region, on the basis of their energy of electromagnetic radiation, and those are given in this table. So you can see here from left to right, these are the regions, and from left to right the frequency is increasing. That means energy is increasing. And in the from right to left, frequency is decreasing. That means this radio wave which have least frequency or least energy, and this gamma ray which have higher energy, highest energy or highest frequency. Okay, so let's discuss about these regions. So first of all, first region is radio wave. Radio wave which have frequency region. This is frequency region 3 into 10 to the 6 to 3 into 10 to the 10. Okay, in this region we will have radio wave electromagnetic radiation. So this radio wave will interact with spin of nucleus. As we know that as like electrons, nucleus have also spin. So when radio wave will interact with nucleus, it will rotate or change the direction of spin of nucleus. Okay, so after that we will have some NMR spectra. NMR spectra means nuclear magnetic resonance spectra. Okay, next, in the radio wave region, when the electromagnetic radiation will interact with electron, it can change the spin of electron, and it will give us ESR, electron spin resonance spectra. Okay, next, moving a step ahead, there is a energy region of electromagnetic radiation which have higher energy than radio wave. Okay, which is the region is 3 into 10 to the power, I have not written here 3, but here there is a 3 here, 3 into 10 to the power 10 to 3 into 10 to the power 12. This is the frequency region of microwave. So microwave will interact with those molecules which are polar molecule. Okay, and again, if the polar molecule have some rotation, and due to which rotation there will be a change in dipole moment. If there is a change in dipole moment, then only microwave will interact with those polar molecule, and it will change the rotational energy. Okay, next, as we know that visible light. What is visible light? It is, we know that VIBGYOR. Okay, from violet to red. Red color has the, or red light has the least energy, and violet has the highest energy. Electromagnetic radiation which have lesser energy than the red light is called IR, which is infrared. We call it infrared. And those electromagnetic radiation which have more energy than violet are called ultraviolet. Okay, let's discuss about infrared. So as we know that in molecule which are made up of atom which have some vibration in different way, they can vibrate in this way. This molecule will go to this direction and again come to this direction, and this atom will also vibrate, or in this way also it can vibrate. This molecule will move like this, this molecule will move like this. Okay, so different type of way are there of vibration. So due to the vibration, it should be there should be a change in dipole moment. Then only that infrared radiation wave or electromagnetic radiation which have the region 3 into 10 to the 12 to 3 into 10 to the 14 will interact with those molecule, and it will change the vibrational energy of the molecule. Okay, next region is visible and ultraviolet. So in this region, the frequency range is 3 into 10 to the 14 to 3 into 10 to the 16. So in this range, the radiation will interact with the valence electron of a atom. okay, only with the valence electron. So it will change the energy of the valence electron, and with the help of this spectra we will know about how much energy we'll have with the atom or molecule, and different type of structure elucidation information we will know about those. Okay, next region is 10 3 into next region is X-ray. Okay, X-ray have frequency range 3 into 10 to the power 16 to 3 into 10 to the power 18. Okay, so in this region X-ray will interact with the inert electron of a atom, not on the valence electron. It will interact with the inert electron, inert shell electron. So it will change the energy of inert electron. Next region is gamma ray, which have frequency range 3 into 10 to the power 18 to 3 into 10 to the power 20. So in this region gamma ray will interact with the nucleus. It is not like this NMR. In NMR the electromagnetic radiation will only change the spin of the nucleus, but in this case in gamma ray will directly interact with the nucleus and it will change the configuration of the nucleus. The particle, that means proton neutron, it will change the configuration of the proton neutron, and there will be a rearrangement of the nuclear particle. After interaction of electromagnetic radiation with matter, what will happen? So width of spectral line means first of all we have to know the basic concept of spectroscopy. So there will be a source of light. This is the source of light from which a light will emit. Okay, and there will after that there will be here a slit. That means a slit means in this slit there will be a narrow hole. Okay, so through this narrow hole the light will travel. Okay, so this is slit, and then that light will come and fall on a sample. This is the sample on which we will observe the matter. That means this is the matter on which we will allow to interact the electromagnetic radiation, and we will obtain some spectra, and that spectra will be detected in a detector. So this is the detector here, detector. So in this detector there are different types of detector are available. So suppose this is the detector where we will obtain a like this graph peak. Okay, so from this light there will be the light will emit different type of frequency. Suppose this is one frequency, this is one frequency. Different type of light will emit. This source will emit different type of light which have different type of frequency or wavelength. So the slit will do what? It will only allow to transmit through the slit only one frequency of light, a single frequency light. It should, but let's see what happens. So it will allow one frequency light and it will fall on this sample, and after that the molecules, as the molecules have atoms which have some energy, different type of energy, and after that those atom or molecule will absorb that light. The energy of the light will absorb. So after that we will obtain a absorption spectra or emission spectra. Okay, so this is the basic concept of spectroscopy. But there is a problem here. It is impossible to modify a slit which can only transmit only one frequency. If it will transmit one frequency, we will obtain like this spectra. There will be a sharp peak like this. But this is impossible because it is impossible to modify one slit, such a slit which have capability to allow only one frequency. It will allow not only one frequency, it will allow several frequency, 2, 3, 4 types of frequency light. Okay, so different type of frequency will have different energy. So as the molecule, as the sample is not a ideal sample. Okay, so if it is ideal, it will be ideal sample, then only it will have only one energy. All molecules of the samples will have only one energy, but this is not ideal. Okay, that's why in different molecules will have different energy, and as the slit is allowing several light of frequency, different type of frequency, so it will different energy molecule will absorb different frequency light. So it will give not only one sharp peak, it will show a broadening. That means there will be a broadening of this peak. Okay, like this. Again, there is another region which is collision broadening. So in a sample, let's consider there are three particles. Okay, there is a one particle here, there is one particle, and this is one particle. So let's consider there are three particles in a sample on which we are going to interact that electromagnetic radiation and going to have a spectra. So suppose this molecule is in rigid state. There is no motion of this molecule. This is 1 and this is 2, this is 3. This molecule, if this molecule is moving in this direction and moving in this direction, 3 molecule, that means these 2 and 3 molecule are moving towards each other. Then what will happen? When they are approaching to each other, then the energy of these 2 molecule will be higher. Okay, so due to this collision, the molecules of a sample will be changed. So there are lots of molecules in a sample, so they are moving in different direction and they are colliding with another molecule, or some molecule are colliding, but after that collision they are moving apart from each other. Okay, so due to this, all those things, the energy of those molecules are changing. Suppose this one molecule is in this spectra. This is one molecule, new one, which have frequency. That means it has some energy which will absorb only new one frequency of light. The coming light which have new one frequency, it will absorb this molecule 1 which have, suppose, this much absorption peak. Okay, now this molecule 2 which have, due to the collision, it will have a different energy from the previous one. So it will absorb, suppose, in this new 2 frequency of light, this 2 molecule will absorb new 2 frequency of light. So it will be like this, and this 3 molecule will absorb new 3 frequency of light. So there will be a broadening like this. And of course there will be some molecules in this sample which have energy in between this v1 and nu1 and nu2 here, and there will be some molecules which have energy in between nu1 and nu3. So those molecules will absorb the similar energy which is coming from the source of light. So there will be a broadening here due to the collision. Okay. Now next region of having a broad peak is Doppler broadening. So what is the Doppler broadening? Suppose there is a sample here. Suppose there is a sample. So there is a one particle which is in rigid state. Two molecule. This is number 2 molecule. This is number 3 molecule. So this molecule is moving in this direction. This molecule is moving in this direction. So basically the thing is that in a sample there are lots of molecules are there, and all molecules will not have the same velocity. They will move in different velocity. Okay, suppose there are 20 molecules are there, and in between this 20 molecule 10 molecules will have suppose 100 velocity. Okay, and some molecules will have which have higher velocity. Some molecules, suppose 6 molecules which have higher velocity than this 10 molecule, and suppose there are some molecules which have lesser velocity than this 10 molecule. So from the Maxwell distribution we can know that there is a graph here. So if Maxwell distribution says that there will be a fraction of molecule, that means a fraction of molecule which have a certain velocity. This is velocity line, velocity axis. So there are a maximum number of molecules which have a certain velocity, and some other fraction of molecule which have more velocity than this most probable velocity. That means there will be some other velocity which have in which the other molecule will move. Okay, so this is the most probable velocity. That means this is the 10. In this case 10 is the 10 molecules, maximum number of molecules are moving in 100 velocity. So 100 is the, in this case 100 is the most probable velocity. So it is concluded that, and having different kinetic energy molecule will absorb different frequency. Suppose in a absorption spectra, suppose there will be frequency v2 and there will be frequency nu1. This is nu1, nu2 and nu3. Okay, these are 3 frequency of light. So this 10 molecule will absorb as 100 of maximum number of molecules are moving in 100 velocity. So the maximum peak will be in the, and if this 10 molecules have nu2 such a energy, if this 10 molecule will absorb nu2 and nu2 frequency of light, then as maximum number of molecules are moving in 100 velocity, so there will be a highest peak in this nu2 frequency. And some other molecules, suppose these 6 molecules which are absorbing nu3 frequency of light, so there will be a 6 molecules will be will give this peak. And for molecules, as it has lesser velocity, so it will have lesser energy, so it will absorb lesser frequency light. So here it will be also a peak. So there are some, if there will be some other molecules will have also present there, then those molecule will absorb in this region of the frequency, so the peak will be broadened. Okay, so peak will be obtained like this. Now, according to Heisenberg uncertainty principle, if there is a mole atom here, this is nucleus and this is one electron. Okay, it is impossible to evaluate both time and energy simultaneously. You can't determine time and energy simultaneously. So suppose if this electron uh, is staying at this point for delta t time. Okay, so then we can't determine what will be the energy of the electron at that time, delta t time. And again, if we know if the electron have delta E energy, so having that delta E energy, for how many time it will have that delta E energy, we can't determine that delta T. So according to Heisenberg uncertainty principle, it is defined as, in mathematically, delta E delta T into delta T is approximately equal to Planck's constant upon twice pi, which is equal to 10 to the power minus 34 joule second. Okay, suppose after allowing to fall a electromagnetic radiation on this electron, then this electron will jump to the next energy state. This is one shell, and this is one shell, which this shell has higher energy than this shell. So due to this electromagnetic radiation, this electron will go to this higher electronic cell. But it is usually experimentally seen that the lifetime for a excited electron to stay in this position in this cell is 10 to the power minus 8 second. Okay, only for 10 to the power minus 8 second the electron will stay here, and after that it will again come to this original shell. So here the delta E will be equal to 10 to the power minus 34 by del T will come here. Okay, so 10 to the power minus 34 upon delta T will be here. So we can write 4 into 10 to the power minus 8. So it will be 10 to the power minus 26. Okay, joule. So 10 to the power minus 26 joule is the uncertainty in energy. Okay, next, so as we know that energy means E is equal to h nu. Okay, so nu means it will be equal to E by h. So in energy, uncertainty is 10 to the power minus 26, and for Planck's constant it will be approximately equal to 10 to the power minus 34. So it will give you 10 to the power plus 8 hertz. Okay, so uncertainty in frequency is 10 to the power plus 8 hertz, but the range of electromagnetic radiation, the range of electromagnetic radiation to absorb a light, electromagnetic radiation for a atom is 10 to the power 14 to 10 to the power 16 hertz. So it is much more lesser than this range. It doesn't fall on this range. So the effect of uncertainty principle of Heisenberg is due to this region, the broadening of spectra is much more less effective. Okay.